It is given the next information. This question asks you to investigate conditions for the existence of complex roots of polynomial equations of degree 3 and 4. The cubic equation x cubed plus px squared plus qx plus r is 0, where p, q, r real, has roots alpha, beta, and gamma. A. By expanding x minus alpha multiplied by x minus beta multiplied by x minus gamma, shows that p is, q is, r is. 3 marks. And according to the remainder theorem, we know that if roots are given, we can rewrite a given polynomial as x minus the first root, x minus multiplied by x minus the second root multiplied by x minus the third root. And the idea is the next. If we open parentheses on the right hand side, then we can equate coefficients in front, same powers of x. So let's expand the right hand side, so it becomes x minus alpha multiplied by x squared minus beta x minus gamma x plus beta gamma, and it is equal to x cubed minus beta x squared minus gamma x squared plus beta gamma x minus alpha x squared plus alpha beta x plus alpha gamma x minus alpha beta gamma. And let's consider terms containing x squared, and we can see that p is negative alpha plus beta plus gamma as required. And equating coefficients in front of x, we can see that q is alpha beta, beta gamma, alpha gamma as required. Alpha beta plus beta gamma plus alpha gamma, and equating just numbers, we can see that r is negative alpha beta gamma as required. The next, bi, shows that p squared minus 2q is alpha squared plus beta squared plus gamma squared. 3 marks. Let's consider p squared minus 2q. So p squared becomes alpha plus beta plus gamma multiplied by alpha plus beta plus gamma minus 2q. So it's minus 2 alpha beta minus 2 beta gamma minus 2 alpha gamma is equal to, it becomes alpha squared plus alpha beta plus alpha gamma plus beta alpha plus beta squared plus beta gamma, and plus gamma alpha plus gamma beta plus gamma squared minus 2 alpha beta minus 2 beta gamma minus 2 alpha gamma. And we can see that alpha beta plus alpha beta minus 2 alpha beta 0, alpha gamma plus alpha gamma minus 2 alpha gamma 0, alpha beta, beta gamma, alpha gamma plus alpha gamma minus 2 alpha gamma also is 0, and hence we can see that it becomes alpha squared plus beta squared plus gamma squared as required. BII hence shows that alpha minus beta squared plus beta minus gamma squared plus gamma minus alpha squared is 2p squared minus 6q, 3 marks. Let's expand the left hand side. So it becomes alpha squared minus 2 alpha beta plus beta squared plus beta squared minus 2 beta gamma plus gamma squared plus gamma squared minus 2 alpha gamma plus alpha squared. And we need, it is given hence, so we should use the previous result to show this, and the previous result is the sum of squares. The sum of squares is p squared minus 2q. So this and we can see that it's alpha squared plus alpha squared, beta squared plus beta squared plus gamma squared, so it's 2 times the sum of squares, hence it will be 2 multiplied by p squared minus 2q, and the remaining negative 2 alpha beta minus 2 beta gamma minus 2 alpha gamma, so it's minus 2, and alpha beta plus beta gamma plus alpha gamma is q, so minus 2q, and it becomes 2p squared minus 4q minus 2q minus 6q as required. The next, C. Given that p squared is less than 3q, deduce that alpha beta gamma cannot all be real. Cannot all be real. We will need this condition. So, if we consider the previous result, and it is assumed that it is given initially that roots are real, and we get that 2p squared minus 6q is equal to this. It's just equivalent for combination of roots, and if p squared minus 3q, p squared is less than 3q, then p squared minus 3q is less than 0, hence 2p squared minus 6q is less than 0, and from BII, if all roots are real, then 2p squared minus 6q is the sum of squares, and hence is, or 2p squared minus 6q must be greater than 0, and since 2p squared minus 6q is less than 0, it means that roots cannot all be, since then all roots cannot all, since then cannot all be real. It's quite easy. If all roots are real, this statement must be true. And this statement looks like some expression is equal to the sum of squares, but sum of squares is always greater or equal than 0. And if this is less than 0, sum of squares cannot be less than 0, so which is impossible, hence all roots cannot be, it cannot be that all roots are real. The next, consider the equation x cubed minus 7x squared plus q x plus 1 is 0. Q is real. D. Using the result from part C, and result from part C is this condition: all roots to be real, we need or actually cannot all be real, we need p squared must be less than 3q. So read again, using the result from part C, and from part C, if p squared if p squared is less than 3q, then cannot all roots be real. Shows that when q is 17, this equation has at least one complex root, 2 marks. And if cannot all roots be real, it means at least one is complex. So to be this true, p squared must be less than 3q. So let's check. P squared is 49, and if q is 17, 3q is 51. Hence p squared is less than 3q, and from part C it's a condition that all cannot, hence cannot all roots be real, and it means at least one is complex. One root, at least one root is complex. Next, Noah believes that if it's his conjecture, if p squared is greater or equal than 3q, then then alpha, beta, and gamma are all real. EI. By varying the values of q in the equation, determine the smallest positive integer value of q required to show that Noah is incorrect. 2 marks. It's definitely true statement that if p squared is less than 3q, then all roots, or cannot all roots be real. And its opposite statement, if p squared is greater or equal than 3q, conjecture is that all are real. And we need show that for some q, this conjecture is not true. And we need the smallest positive integer value of q. We need the smallest positive integer value of q. And let's consider this border value. So let's consider p squared is less than 3q. So what is p squared? It's 49 less than, it's actually, we can use this in this form. P squared is greater or equal than 3q. It's from his conjecture, so 49 is greater or equal than 3q, hence q is less than equal than 49 over 3, which is 16 and 1/3. It's from conjecture, and since q is positive integer, so possible values of q is 1, 2, 3, so on, and up to 16, and we need find the smallest positive integer q, so that this polynomial is this polynomial has at least one complex root. So all it has all three real roots. To disprove this conjecture, to show that this conjecture is not true. And how to do that? We use a calculator, use y, this function for polynomial, and since the smallest possible value of q is 1, let's start with 1, so we consider x cubed minus 7x squared plus 1x plus 1, and the graph looks like this, and we can see 3 points of intersection with x-axis, so there are 3 real roots, and we need consider another value of q, and let's consider some greater, because we need up to 16 and we need the least positive. Let's consider, for example, 10x plus 1, and we can see again 3 real roots. Definitely for q from 1 to 10 also there will be 3 real roots, or actually I don't know, maybe not, but I think that let's increase q, since it is given the least possible value of q, so I think that graph is just moving up. So let's consider 11, and we can see that also, you can see that it is moving, this minimum is moving up, and we need just more. If consider, for example, 13, we can see that only one real root, but we need the smallest positive value, so let's consider 12. And it's the least possible value. We can change limits for x, y to see it more clearly, that the curve doesn't touch x-axis, so to see it clear, and it's clear that it doesn't touch x-axis, so there is only one real root. So the least possible value of q is 12. And the next question. Hence, this conjecture is not correct. So opposite statement is not correct. Statement that if p squared is less than 3q cannot all roots be real, it's always true, but opposite statement is not true. The next EII explain why the equation will have at least one real root for all values of Q. We know that if a complex number is a root, complex conjugate is also a root. Hence, complex roots arise in pairs. And since it's a polynomial of degree of 3, there are 3 roots in total. And hence 2 can be complex, 3 cannot be complex. Hence there are 2 complex and or it may be 0 complex or 2 complex roots at all, and hence there may be 3 real or 1 real root. So anyway, there is always at least 1 real root. The next. Now consider polynomial equations of degree of 4. The equation x to the power of 4 plus px cubed plus qx squared plus rx plus s is 0. PQRS are real, has roots alpha, beta, gamma and delta. In a similar way to the cubic equation, it can be shown that P is, Q is, R is and S is. So again, if we know roots, it can be rewritten as x minus alpha multiplied by x minus beta multiplied by x minus gamma multiplied by x minus delta. And it is equal to x squared minus alpha x minus beta x plus alpha beta multiplied by x squared minus gamma x minus delta x plus gamma delta is equal to 4 by 4 there are 16 terms in total. It will be multiplied by x squared x to the power of 4 minus gamma x cubed minus delta x cubed plus gamma delta x squared multiplied by x squared minus y minus plus. Yes, now negative alpha x is multiplied by, so minus alpha x cubed minus plus alpha gamma x squared plus alpha delta x squared minus alpha delta gamma x. Let's check. Minus alpha x minus alpha x cubed plus alpha gamma x squared plus alpha delta x squared minus alpha gamma delta x, and now minus beta x, so minus beta x cubed plus beta gamma x squared plus beta delta x squared minus beta gamma delta x, and now alpha beta multiplied by x squared, so it's plus alpha beta x squared minus alpha beta gamma x minus alpha beta delta x, and plus alpha beta gamma delta, and we need to show that P is minus n sum. What is P? P it's in front of x cubed, so this this and this. Yes, and we can see that P is minus alpha plus beta plus gamma plus delta as required. Alpha, beta, gamma, delta. The next Q. To get Q, we equate with Q. It's x squared 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes, and all possible combinations. Delta gamma, alpha delta, and so it must be, I hope there is no mistake, so Q must be alpha beta plus alpha gamma plus alpha delta plus beta gamma plus beta delta and plus gamma delta. Okay, and equating just numbers, we can see that S is, oh no, S also needed. S is alpha beta gamma delta, and R is, to get R, equating coefficients in front of X. Where is X? Is this 1, 2, 3, 4. Yes, it's minus. It should be minus alpha beta gamma plus alpha beta delta, all possible combinations, plus alpha gamma delta plus beta gamma delta. Okay, Fi. Find an expression for alpha squared plus beta squared plus gamma squared plus delta squared in terms of P and Q. 3 marks. So we can do it similarly. What did we do for cubic polynomial to show that alpha squared plus beta squared plus gamma squared is p squared minus 2 q. We considered p squared, or actually it was required to show that it's true. Okay, so let's consider again p squared. So p squared becomes alpha plus beta plus gamma plus delta multiplied by alpha plus beta plus gamma plus delta. There are 16 terms in total, and it will be alpha squared plus alpha beta plus alpha beta plus alpha gamma plus alpha delta plus beta alpha plus beta squared plus beta gamma plus beta delta plus gamma alpha plus gamma beta plus gamma squared plus delta gamma delta plus alpha delta plus beta delta plus gamma delta and plus delta squared, and it is equal to alpha squared plus beta squared plus gamma squared plus delta squared, and we can see alpha beta and also alpha beta and also alpha beta, so it's 2 times alpha, beta, and it will be the same for all combinations. So it will be plus 2 times of all possible combinations of the product of two roots, and hence it's q plus 2q. And so hence we get that p squared is the sum of squares alpha squared plus beta squared plus gamma squared plus delta squared plus 2q. Hence the sum of squares alpha beta plus beta squared alpha squared plus beta squared plus gamma squared plus delta squared is equal to p squared minus 2q. So FII. Hence state a condition in terms of p and q that would imply this polynomial of degree of 4, this equation, has at least one complex root. Hence, we can conclude that to have all real roots, or actually it's not correct. It's not correct to say to have all real roots. It's not correct, but if we consider that p squared minus 2q is less than 0, then definitely it cannot be 0 because the left hand side is positive or 0, hence all roots or cannot all roots be real. Cannot all roots be real. Notice that opposite statement is not true, but this statement is definitely true. It's similarly to cubic, and you remember this conjecture that if it's opposite statement, all are real, and this is not true. And for this equation degree of 4, it's also opposite statement is not necessarily true. It may be true, but we don't know. It may be true, but definitely it not must be true. But if p squared minus 2q is less than 0, if p squared is less than 2q, it definitely a true statement that cannot all roots be real. So question was hence state a condition in terms of p and q that would imply given equation has at least one complex root. So it's this condition. Cannot all roots be real, hence at least one complex root. Okay, G. Use your result from part FII, it means this result, to show that the equation x to the power of 4 minus 2x cubed plus 3x squared minus 4x plus 5 is 0 has at least one complex root, 1 mark. So to have at least one complex root, this statement must be true. So let's consider p squared. P squared is 4. pq, q or 2q is 6. Hence p squared is less than 2q. So at least one complex root. Or cannot all roots be real, directly from the previous result. The next, the equation x to the power of 4 minus 9x cubed plus 24x squared plus 22x minus 12 is 0 has one integer root hi. State what the result in part fii, again this condition, tells us when considering this equation. Again, let's consider p squared. P squared is 9 squared, 81, and 2q is what? It's 48. And here p squared is greater than 2q. But we know that opposite statement is not true. Hence, nothing can be deduced. Next, write down the integer root of this equation, 1 mark. Real root, we can directly see as x-intercept. So let's consider this function. Required integer root is -1. Next, by writing x to the power 4 minus 9x cubed, it means this polynomial as a product of one linear and one cubic factor proves that the equation has at least one complex root. So we need rewrite it as, and according to the remainder theorem, it can be rewritten as x plus 1 multiplied by another polynomial. And to find this another polynomial, we need divide a given polynomial by x plus 1. I will use synthetic division, so we write -1 here, coefficients 1, -9, 24, 22, -12, 1 multiplied by -1, -1, -10, sum is -10, -10 times -1 it's 10, so 34, 34 times -1, -34, and -12, 12, 0. It's the remainder, it must be 0, because -1 is the root, and hence our polynomial, this polynomial becomes x plus 1 multiplied by x cubed minus 10x squared plus 34x minus 12, and it is equal to 0, and it's the real root -1. And if we consider this cubic polynomial, the condition for cubic polynomial to have at least one complex root is this: p squared is less than 3q. It's this one, p squared minus 3q, and we need to show that p squared is PQR. P squared is 100, 3q is 34 times 3 is 102, and we can see that p squared is less than 3q, and using the result from the first part, there is at least one complex root. Hence, there is at least one complex root. And that's all for it was HIII 4 marks, and it's the last question, and that's all for this question.